Hello everyone, and welcome to Shelf Life and Packaging webinar. Today's presentation will be 30 minutes, followed by 10 minutes of Q&A. If you have questions during the webinar, type it into the questions pane, and you can submit a question at any time. We'll keep track of these questions submitted to answer during the Q&A. To answer our most commonly asked question in advance, we will be sending out links to the on-demand webinar and the slides to everyone who attended today's webinar. Those will be available a day or two following the webinar. Now I'm going to hand the microphone to Mary Galloway and Dr. Zachary Cartwright, both food scientists here at Meter Group, who will be today's presenters.
Hello, good morning. I just wanted to say welcome to Zachary Cartwright, one of our new food scientists that we have added to the Meter team.
Thank you, Mary. I'm going to go ahead and start us off this morning. So just going over the content. So today we're going to go over what shelf life is. We're going to talk about the things that end shelf life. We'll discuss what a critical water activity is. Mary is going to briefly discuss accelerated shelf life testing. We'll go over a shelf life example using KALE chips. And then we'll end with talking about how ingredient changes affect shelf life.
All right, so what exactly is shelf life? Well, normally we think of it as an expiration date or a use by date. Really, shelf life is the time during which a product will remain desirable. Now, this means it can have changes, but it's at a point where it is no longer desirable or acceptable to a consumer. So these involve sensory characteristics, chemical stability, physical properties, microbiological properties, so mold and other microorganisms, and it still needs to comply with nutritional labeling. So if we have a vitamin quotient in there, then we need to make sure that it stays that way. There are three main factors that influence shelf life. So we have the microbial properties, chemical changes, and physical deterioration. So microbial properties obviously is like mold or potentially hazardous bacteria that will grow. Chemical changes, so browning, oxidation, enzymatic reactions, those things like that, and physical deterioration. So we're talking about changes in texture or a caking and clumping issue, moisture migration, those kinds of things. So this can be intrinsic within the product itself, how it's formulated, or extrinsic, which would be related to like storage conditions, the humidity that it's stored at, the temperature, and what type of packaging that the product is put into. All of these factors are actually connected to water activity, and I'd like to go into that a little bit more. So here we're going to have a stability diagram that is looking at water activity versus moisture content, and also a rate, so you can think of moisture content as well on the y-axis as an increased rate of reaction. So first we're going to start here with the moisture absorption isotherm. This is just a generic one. Dr. Ted Labuza put this stability diagram together, and we just want to show here where a standard kind of very, very generic moisture isotherm would be on this graph. Next, we have where the microbial growth will happen. So we have mold growth, yeast, and bacteria. And you can see as those increase in water activity, so does the rate of that growth also increases exponentially. Next, we have where the chemical changes will happen. We have some interesting trends here. You can see the normal trend for enzymatic activity that will increase as the water activity increases. But we have some unusual trends here for lipid oxidation, which we've talked about in other webinars, where the lipid oxidation at very low water activities is very high, but then as it increases to about 0.2, 0.3, 4, 5, it's the most stable. And then after that, after about 0.5, then it starts to increase again. Also, we have interesting reaction for browning reactions that actually peaks around 0.6. And lastly, we want to talk about physical deterioration. So in this range, about 0.3 to 0.5, we'll have a loss of crispness, powder caking, and then collapse of the matrix of the food. So this is where we're going to see the changes in texture and things like that we talked about briefly.
So next I'll be discussing why does shelf life end, and also what is a critical water activity. So first you need to figure out what the mode of failure is for your product that is ending shelf life. And this can be due to a variety of reasons. So this could be due to microbial growth, so growth of yeast or bacteria or molds. It could be due to rancidity in your product, perhaps changes in texture. So that could be caking and clumping or maybe crystallization. You could have vitamin degradation leading to the end of shelf life, changes in color, and also enzymatic reactions such as browning reactions. So each of these different modes is associated with a very specific water activity, and this water activity is known as your critical water activity, or RHC. So critical water activity is the water activity at which an undesirable change is going to occur in your product. And this can be physical changes, and these are identified by a change in the sorption properties of your product, ultimately resulting in a change in texture. So again, that may be caking or clumping or perhaps crystallization. So your critical water activity is actually temperature dependent, and as you increase the temperature of your product, your critical water activity is going to decrease. And this means that your product is going to be the most stable below the critical water activity. So it's important that you know that critical water activity so that you can try to stay below it through your production. So to the right here is a graph showing several different isotherms that Mary put together for us. So again, we are looking at water activity along the x-axis and moisture content along the y. And so we're going to look at the different critical water activities for these variety of products. So for milk powder, you have a critical water activity of about 0.42. So you can see at about 0.42, you get a much larger increase in moisture content with a small increase in water activity. And this is where caking and clumping will start to occur. Milk powder is interesting because it has a second critical water activity between 0.7 and 0.8, where crystallization starts to occur. For cereal, its critical water activity is there in blue around 0.5. For grain-free kibble, it's closer to 0.7 because of microbial growth. Pet food companies have to stay below that level. And then sucrose here, you can see that its critical water activity is all the way up at about 0.85, where you have a sudden increase in moisture content with just a small increase in water activity. So the critical water activity must be identified for your product. And remember that water activity is going to affect the growth rates or the reaction rates for each of these different factors. So increased water activity results in increased rates. That's something to keep in mind. And the critical water activity must be identified for a product before the shelf life can be determined. And this is something that we'll go through in our KALE chip example in a few slides. So for each mode of failure, you have to assess why these are occurring. So for microbial growth, you need to keep your water activity below 0.7. If rancidity is your mode of failure, then you need to be measuring your oxidation levels. If change of texture results in ending your shelf life, you will need an isotherm, like we just discussed. For vitamin degradation, you need to measure your vitamin levels. Changes in color can be assessed using colorimetry. And finally, enzymatic reactions can be assessed by looking at enzyme activity.
So now I'd like to talk about an example of accelerated shelf life testing. Now, accelerated shelf life testing can be a little complicated because of the fact that you have to determine your mode of failure and be able to track that. So I just wanted to talk about some of the key objectives when you're doing and setting up an accelerated shelf life test method. The purpose is to obtain empirical data for your specific product. And this is important. Sometimes shelf life can be determined by looking at similar products on the market and then relating that shelf life to your own. But it really is best to look at your specific product, your specific final product when determining shelf life. So we want to get the empirical data on that. And we're going to relate this to when the product fails at a temperature-dependent RHC. So we briefly talked about that it matters RHC will decrease as the temperature increases. Makes sense because as you're putting more heat into the system, you're adding energy, and that reactions will happen faster. So the RHC is going to go down. So how to set one up? You need to select 3 different water activities and 3 different temperatures. And then what you would do is you would hold your product at a combination of each of these 3. So it would end up being like 9 subsamples for these combinations. And then you're going to track the progress of the mode of failure. So if, let's say, you're doing lipid oxidation, you need to measure the oxidation level. And you also need to determine when that's going to fail, because like I mentioned before, you can have some changes in your product and still be within your shelf life. It's at the point where it's undesirable or not acceptable to the consumer anymore. So you have to decide when that is going to happen. Things are going to change with products, such as happens, but you have to determine when that is no longer acceptable anymore. And then we collect time versus quantity of change to determine the rate. And then after we're all done with that, then we're going to model that collected data, accounting for both time, temperature, and water activity. And when we get this correlation, we'll be able to model the shelf life and the reaction of the rates for your mode of failure. So to explain it a little bit more as an example, I'm going to talk about one that we have done a few years ago, infant formula, and how we set it up and how we went through it. It is actually a fairly complicated process. There are lots of books and articles about accelerated shelf life testing. And as a matter of fact, this example I'm going to be talking about was published and can be found in the Shelf Life International Meeting of 2017 in their proceedings. And we'd be happy to give a copy of that if you'd like to know more. But I'll go through it just a little briefly so you get kind of an idea of what's involved. So we had the infant formula and we held it at 3 temperatures. In our case, it was 30, 37, and 45 C. That was, we can do these testings at accelerated shelf life. So that's the accelerated part, is that we're going to elevate the temperature and the water activities and see what happens to kind of make things progress a little faster. And then we had 3 water activity levels. We had 0.43, 0.50, and 0.65 water activity. And so we did a combination of those, end up with 9 different subsamples that we were monitoring. And what we would do for the temperatures is we'd have them in sealed containers with a saturated salt underneath that would produce that specific water activity we were interested in. And then we would put them in ovens set to the temperatures we were looking at. And then we would monitor the changes. So for this, we had lipid oxidation as the mode of failure for the infant formula. And we were tracking T-bars to determine when oxidation had reached an unacceptable level. And for us, the unacceptable level was 1 milligram of malonaldehyde per kilogram. That was considered unacceptable. Then we looked at the reaction rate for each of those temperature and water activity combinations, and then we determined that by using the slope of the time versus the T-bar value. And in this case, it's a linear relationship, so it makes it really nice and easy. That's not always the case. Sometimes it's this is what we call a 0-order reaction, but it can be a first order. Which means it has more of an exponential look or a natural log look. It all kind of depends. But for us, this was a linear relationship and made it very simple. Like I said, again, if you are interested in that more, how we did that study and the data, please let us know and we will be happy to send that to you. I also did put in the resources at the very end of our webinar what that was. It was called a hygrothermal model, time model for infant formula. Now we're going to talk about the shelf life example of kale chips. Now this is, we picked this one because it's a little more simple, so it kind of gives you more of a thought process on how to go about determining shelf life. Also, you'll see with the kale chips, one of the modes of failure is loss in texture. And that tends to happen, if you go back to our stability graph, that tends to happen pretty early, pretty low in water activity. And so that tends to be a very common mode of failure for shelf life. All right, so here we have some nice, beautiful kale chips. and some not so nice kale chips here. The manufacturer had this one as the shelf life was only 30 days. And their issues were that they had a loss of texture, which I mentioned before, and also mold growth. So we actually have two modes of failure in this example. So how can we increase the shelf life? 30 days made it difficult for them to ship their product very far, so they wanted to increase that. So what ended shelf life? This is where we have to determine that mode of failure. For us, we had microbial growth, and we also had a loss of texture, so we had both of those. Now, what water activity are the chips at risk for microbial growth? And we know from prior information that if we can keep our water activity below 0.7, we will not have any microbial growth. So where are they at risk? Well, anything above that, so anything above 0.7. At what water activity do the chips lose texture? Well, we don't exactly know at this point. So what do we need? We need an isotherm, because an isotherm is going to be able to tell us when we're going to see that change in texture. So here is a isotherm for a kale chip with water activity along the x-axis and moisture content along the y-axis. Now, if you're just visually looking at this, you could probably kind of guess maybe where that loss of texture, it's going to be an inflection point in that trace where we see the adsorption properties really increase, so really a large intake of moisture content. But it is a little tricky to exactly identify that, and it's important that we do. So the simplest thing is to actually go through and do a second derivative evaluation on that slope. So basically what it does is it evaluates the slope to see when the change happens in the slope. It's very easy. And we can see when we look at the second derivative on the right, that right there, that first little peak is going to be our RHC. And you can see when you look back to the isotherm on the left that it correlates very well. When you visually see it, you're like, oh yes, that's where the RHC happens. But it's best to do the second derivative to let you know. Sometimes they're not always obvious. So having this mathematical way to actually calculate that is very, very helpful. Now, if we can keep the kale chips below this critical water activity of 0.7, then they will maintain their crisp texture because we've already identified that for the texture part. And we know that if we can keep it below 0.7, which 0.57 is definitely below that, they are no longer susceptible to microbial growth.
So now that you know your critical water activity, we can start to talk about some of the shelf life calculations. So to predict the shelf life of a product, the equations are going to take into account several different factors. And one of the first factors is the packaging of your product. So the packaging of your product is going to have a water vapor transmission rate. This may be a term that you're familiar with, but just in case you're not, we have a small graphic off to the right to help better explain it. So in any environment, you have a certain amount of water in the air, and the packaging that you choose for your product is going to only allow a certain amount of that water to pass through your packaging and interact with your product. And this is generally measured in grams per meter squared per day. And so your packager is going to test that packaging under certain conditions. Generally, these conditions are around 38 degrees Celsius and 90% relative humidity. So those conditions are going to come into play for our calculations. So in addition, you need to know the surface area of your packaging in meters squared, and you're also going to need to know the mass of your product in its package. There are a few other things you need for these shelf life calculations. So you're going to need to know the storage conditions. So this includes the temperature, the humidity, and then also the atmospheric pressure. So the atmospheric pressure is going to largely depend on your elevation and then can also vary with differences in weather. And then finally, you're going to need to know your water activity. So this includes the initial or the current water activity of your product, and then also the critical water activity, which we just determined a few slides ago. So there are several equations that go into these shelf life calculations. We're not going to go into them into any great detail today, but if you have any questions about the calculations, please feel free to reach out to us. So we're going to be looking today at a shelf life calculator that we use here at Meter Group that is in our moisture analysis toolkit. So these are screenshots directly from that software. So the first thing you're going to want to do is enter your water vapor transmission rate, testing temperature, and humidity. And as I mentioned, this is usually about 38 degrees Celsius and 90% humidity. And then next you're going to enter some information about the storage conditions of your product, and then also some information about the product itself. So we're just going to go through this step by step. Let's say in this example you placed your product somewhere with 60% humidity, 100 kilopascal for your pressure. Let's say that you have 1 pound of your product, so 454 grams. Let's say you take that product, you place it somewhere that's 30 degrees Celsius. You calculate the packaging area or the surface area for your product, and that your current packaging has a water vapor transmission rate of 7.5. Next, you input your initial water activity, so in this case about 0.45, and then finally you enter that critical water activity, which we calculated using the second derivative of the isotherm, which was 0.57. So using the software, you can go in, quickly select your previously saved isotherm file. You come down here and navigate to the calculate button, and the software is going to give you an estimated shelf life. So here it is, that shelf life of 30 days that we had talked about before. But how can we extend the shelf life? 30 days is not very long, and I'm sure the manufacturer would want something much longer. And so in order to change the shelf life and to extend it, we are going to look for packaging with a smaller water vapor transmission rate. And so there's another calculator in the moisture analysis toolkit designed just for this scenario. So once again, you're going to put in your water vapor transmission rate, temperature, and humidity. And then next you're going to enter your desired shelf life. So let's say that we want a desired shelf life of 180 days instead of 30 days. So we'll go ahead and put that in. And then once again, enter the same storage conditions. So same humidity and temperature, same initial water activity and critical water activity, same total dry mass, so 1 pound, same atmospheric pressure, and same surface area. So everything is the same here, just we're changing our desired shelf life. Once again, you just use your previously saved isotherm file, navigate to the calculate button, and this is going to tell you the water vapor transmission rate that you need for that shelf life. So here our result is 1.3 grams per meter squared per day. So you could take this information to your packager and tell them that you need something with this WVTR to achieve your desired shelf life. So I'm going to let Mary go over this table about different water vapor transmission rates for packaging materials.
Yes, I thought it might be interesting to see where some of our common packaging materials might compare with one another. This is a table I've got from the Encyclopedia of Food Science and Nutrition. There are actually more various polymers on that chart. I just put a few in here so you could get a good idea. You can see that there's kind of a big range here. I wanted to point out a few things before I go over the table that's important to know. For these water vapor transmission rates, they were done at 38C and 90%, relative humidity. That's not always the case, and it's important to know because that's part of the calculation. Sometimes they're, let's say, 30C and 75% relative humidity, but that's part of the definition, like I said, of actually calculating this water vapor transmission rate. Now, the good news is that you're able to change that, as Zach was talking about the software, that you can easily put in the conditions where that was calculated. The other thing I want to point out too is the units. So this is in metric units, and that's how the software works with it as well, this grams per meter squared per day. Sometimes it's grams per meter squared per 24 hours, or it's in standard units as in inches squared and that kind of thing. So it's important that you have your units correct when you're inputting your WVTR for your packaging material. The other thing I wanted to point out, a couple interesting things here, is that I want to look at the third one here is polypropylene, and this is just a cast, really simple polypropylene. You'll see that it has a WVTR of 8.2, but if you go to the one below it and you have a polypropylene that's oriented, that's just the way it's made, and then it's also metallized, it has like a foil layer into it, that water vapor transmission rate drops already to 1.0. Also, look at the second from the bottom. You can see that if you have a PVC copolymer, that WVTR goes way low to 0.6. So it's important that you know what kind of packaging you're in need of. You don't want to have it too light, as Zach's example showed before, with having a packaging of 7.5. They were only able to maintain the product for 30 days. But if they can find packaging that will drop it to 1.3, then they can make it last for 6 months. That's the big difference. However, you don't want to go too far either, because the lower the WVTR, the better, and you pay for that. So if you're over packaging, you're paying for packaging you don't need. So it's good to understand how packaging influences your product. Better isn't always necessarily the way to go, especially if you have something else. Now, that is going to be your mode of failure. As an example, we're talking about vapor getting into the product and changing it that way, but we could have internal changes as well, like oxidation. You'll notice, like for potato chips are a good example, they have a foil lined packet that helps insulate them from light and the moisture, but they also have oxygen that will create that lipid oxidation reaction inside the chip itself. So they'll generally fill that package with like nitrogen so that they remove that. So those are kind of a lot of things that are involved with packaging, but these are all good considerations.
And I'll add, since we're on WVTR, we had 2 questions just come in. So I will mention that the surface area of your packaging is just calculated by simple geometric size for these calculations. And if you don't know the water vapor transmission rate, your packaging supplier should be able to give it to you. So our last topic for today is the effect of ingredient changes to shelf life. So for this, you can calculate the final water activity of a mixture or a recipe without even making the product. But this requires an isotherm for each of your ingredients. But for today's example, we're going to talk about adding ingredients and how they are going to change the critical water activity for your product. So for example, if you're going to add some ingredients or maybe some seasonings to your final product, this is done in the moisture analysis toolkit using the DLP method, which is an adaptation of the KALE plot, and it's much better at characterizing complex isotherms. So this requires much more or more mathematical steps than the KALE method, but this work is already done for you in the software. So I thought it would be helpful to look at exactly what this looks like in the software itself. So to the upper left is where you're going to add your different ingredients, and then the bottom left is where we are going to get some results. So let's say we have our kale chips. You put in its initial water activity and moisture content, and let's say once again we have 1 pound of these kale chips, and we want to know what happens to the water activity when adding 5 grams of garlic powder to this product. So once again, you just simply navigate to the calculate button. You hit and calculate, and it will give you a new final water activity. So you can see that the water activity came down slightly. The software will also tell you about the final moisture content for the kale chips and garlic. And then off to the right, the software is going to show you how these isotherms are being combined. So the kale chips are that blue trace near the bottom. The garlic is the green trace near the top. And then the program will show you a combined isotherm here in red to show you how those are being combined, and then show you where the equilibrium water activity is, so at 0.449. And so you can start to see how this tool can quickly give you an idea of how added ingredients are going to affect final water activity. So let's say in addition to the garlic, we also add 3 grams of pepper and then 10 grams of like a cashew powder to coat these kale chips. So once again, hit calculate. This time you'll get a new final water activity value of 0.445. So you can see that your water activity is starting to come down with these added ingredients. Once again, you'll have new final moisture contents for each of these products. And to the right, you can see how these isotherms are being combined to give you that answer. So again, the garlic and kale chips, this time we've added pepper, the red trace, and the cashew powder, the purple trace. You can see how these isotherms are being combined in this gold or yellow color. And then the program will tell you the equilibrium water activity at 0.445. So you can see how this software tool can really speed up your R&D processes and give you an idea of how your water activity is going to change.
All right, we're almost done here. In conclusion, I'd like to talk about some of the steps that we need to consider when we are determining shelf life and packaging. So first, we want to identify what ends shelf life. That's the number one thing that we need to start with, is figuring out the mode of failure. And then we need to pinpoint the critical water activity. Now, if it's texture related, caking, clumping, moisture migration, that kind of thing, or if it's a microbial growth, those are really easy. We understand quickly how to get the critical water activity for those. For the texture, running an isotherm tells us very fast and can very consistently where that RHC is going to happen. If it's a different mode of failure that we talked about before, like the browning, a change in color, lipid oxidation, any of the enzymatic or possibly vitamin degradation, then we need to perform accelerated shelf life testing. And we went over that before. Next, we need to determine what is your desired shelf life. What do you want it to be? You can either use a change in formulation if you need to adjust things down lower to keep it in a safer range, or you adjust your packaging to be able to preserve your product as you manufactured it. We also need to calculate the proper packaging. And one of the things I forgot to mention when I was talking about the table before is thickness also matters of the product. So the table I showed before, everything was normalized to around 1 ml, but it matters. If it's thicker, it does a better job of becoming a barrier for that moisture. So that's part of determining what's the proper packaging. If you are going to have some formulation changes, then you need to reassess your shelf life and the packaging for that, because things will change if you change the formulation. In Zach's example, he was able to add spices and things without too much change to the formula. It would be hard to know that without isotherms, but a lot of times they do. And if you're changing, let's say, to a cleaner label or wanting to be reduced sugar, sugar has a really great ability to hold on to moisture. And so if you reduce sugar and replace it with something else that isn't as effective, then it's going to change the isotherm. It's going to change how it absorbs moisture and holds on to it. So if you want to maintain, let's say, the same texture and the same flavor, but reduce your sugar, that's going to be more difficult, and you really need to reassess your shelf life calculations and the packaging after that formulation change. Now, if you haven't already done the shelf life testing, you need to make sure that after you've done all your predictions, because they are predictions, they're very handy. The software is really great at just manipulating things very fast and giving you a quick response. If you decide that your storage conditions are changed, you can just change that and recalculate it. But they are indeed predictions off mathematical equations. So you need to get some empirical testing to prove that your shelf life is going to actually fulfill what you want it to fulfill. So here are a few resources. That up at the top there is that hygrothermal model for predicting shelf life in infant formula that we talked about before, that we had done here, and some other examples that you might, some other literature that you might find useful in trying to solve your own shelf life issues. All right.
Awesome. Thank you, Mary. Thanks, Zachary. So we're going to take a few questions here now. There's still plenty of time to type in a question in the questions pane. We'll try to get to as many as we can right now. If we do not get to your question that you've asked, we do have them recorded, and we'll be able to get back to you via email in the next couple of days. So don't worry if we don't talk about your question specifically in the next couple minutes. It looks like we have maybe about 5 to 10 minutes to answer questions here. Let's do, Mary and Zachary, let's take a couple of these and kind of squish them together here, because there's some that they're asking about the software that you guys are using. So is this new software? What is it called? And the isotherms that are used, incorporated into the software, is it something that they have to use meter foods or Aqualab instrumentation with, or can they use something else?
Sure. So the software we were talking about today is the Moisture Analysis Toolkit, and that works directly with our Vapor Sorption Analyzer, or the VSA. So the VSA is what we use to produce isotherms here at Meter. It's certainly not the only vapor sorption out there, but it is capable of producing both static and dynamic isotherms. So you are able to make your own isotherms if you can collect water activity and moisture content data, but our VSA makes it much easier for you to take about a 2-gram sample and place it in a chamber, and after about 48 hours or longer, you can have a complete isotherm with hundreds of points on it, and then you can use the isotherm to predict the shelf life and find your critical water activity, along with several other tools. Do you have anything to add, Mary?
Yeah, I was just going to say that when Zachary mentioned the static versus dynamic is the one that we're showing you where you can find the critical water activity. The sample is not held at a specific humidity and temperature. It's held at the same temperature. That's the ISO part of the isotherm, but it's pushed through, it's exposed to humid air at a specific flow rate that we determine, and then that makes it very easy to clearly see when those changes happen. If you have a sample that you produce an isotherm from a different instrument or on your own, you can actually do it a very old school way where you put your sample in a humidity chamber and monitor the weight change, and when it stops changing weight, then you measure that related to the water activity. That will happen is that the sample gets pushed through those transitions. You don't actually get to see them in live time. So the DDI examples that we were talking about, that dynamic dew point isotherm, is really critical when you're trying to determine your RHC, because if you do it the other way, the DVS, the static way, the sample goes through it during a hold period, and you don't actually get to see when that happens.
Awesome, thanks. Let's see here. How does shelf life change if the product is stored at high temperatures?
Yeah, that's a great question. So as we mentioned before, as you increase your temperature, your critical water activity is going to decrease, which means that your shelf life is going to decrease. And then in addition, as you increase temperature, the water activity of your product is also going to increase. So you can have opposing forces here. You have your water activity of your product increasing and your critical water activity decreasing, which means that overall your shelf life is going to decrease.
Okay, we had another one come in that was asking about, I'm going to move back up here. So asking about the second derivative that you were taking. I'm going to take a bit here. I want to find, I do want to find that exact slide so that we can address this. So the question concerns kind of the changes. Here we go. So the changes here, because we see on the right graph that we have following that 0.57 point, we have a lot of movement up and down that seems much more drastic than what is going on at that first 0.57 point. So the question is, shouldn't we be more concerned about the other stuff, if I'm understanding the question, as opposed to just that first change that we're seeing there?
Yeah, no, that's a great question. So basically, the second derivative is just a mathematical calculation that's evaluating that change in slope. And that's a really good point. What we are seeing is with the first peak here at 0.57, you're starting to see the first changes in the sorption properties. So that's where we're going to focus, because after that, things are changing already. That's when they start to change, and they're going to continue to change. And so if we can keep our product below that 0.57, that's where it's going to be stable. Other things are going to be happening. You can see every time there's a peak or valley, that means there's a change in the slope that it's evaluating. And so you can see at about 0.75, there's another larger peak. And you can visually kind of look at it basically at this point. So we can see, maybe if we explain this in kind of descriptive terms, at 0.57, we're going to start to see that loss of snap of that KALE chip. But as we continue up around 7.5, we're going to start seeing it maybe start being a little more soggy. So it's going to continue to lose its texture, but at a higher rate. So after about 0.75, it's going to be kind of nasty after that. So hopefully I explained that well enough.
Awesome. I think we just have time for one more, and this is just a general one, just asking, how hard is it to create an isotherm for their product?
Sure. So if you have several months and a lot of desiccators, then you can set up an experiment in your lab or wherever you are. And in each of those desiccators, you'd have different salt solutions, and you would have to wait for your product to come to equilibrium in each of those chambers. So this would take you several months. But if you have a vapor sorption analyzer, like I mentioned earlier, you can just take your sample, and after 5 minutes of prep, you place that in the VSA chamber, and you can walk away. And after about 48 hours or slightly longer, you'll have that complete isotherm for your product.
Yeah, and this is actually a service that we offer here. We do have lab services. We have VSAs obviously to sell, but if you're interested in just testing this out, we have lab services, and you are able to send a sample in and have us test it for you and give you the results for your product.
Awesome, great, thanks, Sue. We want to thank everybody for attending today. We're out of time. There are a lot more questions that have come in. We will get back to those. We have them recorded. We'll be able to email you answers to those. Mary and Zachary will be able to correspond with you. If you do have any other questions, please feel free to contact us here at Meter Group. We do have sales support. We have Mary and Zachary that will be able to answer any and all of your questions. I'm going to volunteer you to do that. But also, we will be sending out a copy of the presentation as well as the slides. Those will be available in the next couple of days here. And once again, thanks for joining us today, and hopefully you'll be able to continue your interest in this subject and related ones. And please fill out, if you can, the post-webinar poll. We have a survey just asking about your feelings about this webinar, and if there's any other subjects you'd like to see addressed. And please stay tuned for future Meter Food webinars, and have a great day.